Hello everyone and welcome back. Today I will continue talking about reactions in aqueous solution. As always, I'll provide a link in the description of the video to download the material. So we talked before about precipitation reaction. Today I will talk about acid-base reactions. What are the properties of acids and bases? First, acids have a sour taste. For bases, it have a bitter taste and soapy feel. Acids and bases have ability to change the color of certain dyes. Amber color of tea is lightened usually by addition of lemon juice, which is an acid. Litmus produced from lichens, a composite organism that arises from algae, change its color into red color with acids, while it change its color into blue with bases. For acids, they are substances that ionize into water to produce hydrogen ions. It have a sour taste, like I said before, like vinegar, and it causes a change of litmus paper from blue into red. It reacts with metals to produce hydrogen gas. So example for that would be the reaction of hydrochloric acid, which is an acid, with magnesium, which is solid metal, to give me magnesium chloride plus hydrogen gas will be evolved. It also reacts with carbonate and bicarbonate to produce carbon dioxide gas. Example for that, the reaction of hydrochloric acid with calcium carbonate to produce calcium chloride with water and carbon dioxide, which also will evolve. For bases, they are substances that ionize to produce OH ions. They have a bitter taste, feel slippery feeling. For example, soap. It causes litmus paper to change from red to blue, and their aqueous solution conduct electricity. Brønsted acids and base. In case if we don't have aqueous solution, so we cannot name Lewis acids and Lewis base, we can name them Brønsted acceptors and Brønsted donors. For Brønsted donors, they are the acids, and Brønsted acceptors are the bases. Example, if I have something like hydrochloric acid, it would ionize into hydrogen ions and chlorine ions. So I can also write it in case if I have aqueous solution to be hydrochloric acid to form hydronium ion and chlorine ions. The reason for that because hydrogen ions are very small, they don't exist in water separately as separate moiety. Instead, they are just attached to water molecule to form hydronium ion. Acids can be monoprotic acids, example for that, like we've seen before, hydrochloric acid, which is ionized into hydrogen ions and chlorine ions. For diprotic acid, example for that would be sulfuric acid. Sulfuric acid ionized into two hydrogen ions and sulfate. This actually happens on two steps. In the first step, sulfuric acid ionized by giving away one hydrogen ion and forming HSO4. Then the HSO4 would give away the second hydrogen ion, forming SO4 2-. The third one is the triprotic acid. So the triprotic this means it will give away 3 protons. Example for that is phosphate. Hydrogen phosphate Ionize on us 3 steps. In the first one, it gives away one hydronium ion and it forms H2BO4 minus. Then H2BO4 minus will give away another hydrogen ion forming HBO4 2 minus, and the HBO4 minus will give away the last hydrogen ion forming BO4 3 minus. We here mean by these hydrogens, we mean by that the hydronium ions, but it is easier for us to write down H plus instead of writing H3O plus. Brensted bases, those are the ones that will accept protons. Example for that, if I have sodium hydroxide, it will be ionized into sodium and hydroxyl ions. As for barium, it will be ionized into barium ions and 2 hydroxide ions. Those hydroxide ions actually accept a proton from water, so it will take away proton from water, forming again H2O, which is another water molecules. Those are 2 strong bases, while for ammonium is a weak electrolyte. This is why it is considered to be a weak Brensted base. The ammonia react in presence of water to accept 1 proton from water to form NH4 ammonium ion plus OH minus. So the types of acid-base reactions is divided into either I have a strong acid that would react with a strong base. In that case, the strong acid will give away proton and the strong base will have hydroxide ions. Or I have weak acid that can react with a strong base. In that case, the weak acid will be referred as HB, and the strong base will still remain the OH hydroxyl ions, and if they reacted together, they will give H2O plus B plus. As if I have a strong acid that reacts with weak base, I will consider the strong acid to be still giving away hydrogen ion, and for the weak base to contain only B minus, and the reaction of these two would give me pH. So now let's look at this example. Classify each of the following species in aqueous solution as Brensted acid or Brensted base. The first one, HBr. HBr in aqueous solution, it will give away 1 proton and Br negative. Because it gives away 1 proton, we consider it to be Brensted acid. The second example, NO2 minus, it would accept hydrogen ion forming HNO2. Because it accepted 1 proton, in that case I would consider it to be Brensted base. The third one, HCO3 minus, first it can accept 1 proton forming H2CO3. In that case I would consider it Brensted base. But it also can lose the proton that it have here, forming H plus and CO2 2 minus. Because it lost here 1 proton, I can consider it to be a Brensted acid. Usually we refer to the species that can act as a base or acid as amphoteric. So HCO3 have amphoteric nature where it can accept a proton, and by that it will act as Brønsted base, or it can accept or it can lose one proton and become a Brønsted acid. Acid and base can react together in what we call a neutralization reaction. The neutralization reaction usually results in salt and water. Example for that, the formation of table salt. So the reaction of sodium hydroxide with HCl, it can forms NaCl, which is a table salt plus water. If I try to, this is my molecular reaction. If I try to write my ionic reaction, it would be Na plus and OH minus and proton plus Cl minus to form Na plus Cl minus plus H2O. If I cancel the spectral species in both sides, the Cl and Na, this means my net ionic equation would be written as H plus OH minus to give me H2O. This is the net ionic equation for any strong acid and base that react together. You have to remember sodium hydroxide is a strong base and hydrochloric acid is a strong acid. For a weak acid that can react with a strong base, in that case I can represent it as example. Let's take an example. If I have hydrogen cyanide that can react with NaOH, in that case I have here sodium hydroxide, which is a strong base, and the HCN, which is a weak acid. The reaction of that would form H2O plus NaCN. If I try to write, this is my molecular equation. If I try to write my ionic equation, it would be HCN, which doesn't dissociate that much, and I have here NaOH, which will be written as Na plus and OH minus to give me H2O plus Na plus Cn minus. If I cancel the spectator ions, here I have the Na with the Na, so I end up by the net ionic equation to be HCN plus OH minus to give me Cn minus plus H2O. So the net ionic equation for a weak acid with a strong base, in that case I can write the strong base as OH because I end up by this one, and I always have water in the product. So if we looked at the acid-base neutralization, we usually use it to do what we call titration. Titration is a reaction between the acid and base to know the concentration of one of them. If I have something here, like if I have a base with a known concentration, I put it in a pyrite and I put a certain amount of the acid that I don't know the concentration of this acid. So if I put here the unknown concentration while I use here a known concentration, then I start to titrate in the presence of indicator. Indicator, it has this ability to change the color. So like we see here, it changes the color from when it was just acid. After adding a few drops of the base, it changed its color into pink, and we know by that the end point of this titration. Usually what happens, the hydroxyl ions that comes from the base mix with the hydrogen ions to form water, and with a known concentration. Once the whole number of protons inside the solution of the acid is used up, this is when the color will be turned into will it change from like here in colorless into pink. This will give me an indication of how much amount had been used. So the equivalent point usually is a point that reached when number of moles of the hydroxyl ions is exactly the same number of the proton ions. And this is why neutralization reaction we use it actually, because it can result in ionic compound and possibly water. Example for acid-base neutralization would be the reaction of hydrogen fluoride plus potassium hydroxide. This would give me potassium fluoride plus H2O. Also, the famous sulfuric acid with the famous reaction of sulfuric acid with NaOH to give me sodium sulfate plus water. We could see that in all those reactions water are produced. So let's look at the example here to see how we can use a titration experiment to find out the concentration. In a titration experiment, a student finds that 23.48 ml of sodium hydroxide solution are needed to neutralize 0.5 of KHB. KHB here refers to potassium hydrogen phosphate. What is the concentration in molarity of the sodium hydroxide solution? Because I have here the number of grams, and if I know the molar weight of KHB, which is equal to 104.2 grams, I can find out the number of moles of KHB. So first, the number of moles of KHB would be equal to 0.54 66 grams multiplied if 1 mole KHB contains 204 grams KHB. This would be equal to 2.678 multiplied by 10 to the power minus 3 moles. So from here I could see that KHB reacting against NaOH, because this one contains only one hydrogen and here I have one hydroxyl. This means the reaction is 1 to 1. So the number of moles of KHB is actually equal to the number of moles of NaOH. So if I assumed that this is the number of moles not just for the KHB but also for the NaOH, I can find out the concentration. So the concentration or the molarity of NaOH would be equal to the moles, the number of moles over the volume. So here if I try to write molarity of NaOH, it would be equal to the number of moles, which is that one, multiplied by 10 to the power minus 3 mole over the number of ml. So the number of ml here, it's in milliliter, so I have to convert it into liters. So I multiply here by 23.48 ml if 1000 ml actually contains 1 liter. So if I try to do this calculation, I will find out that the answer is 0.1141, and this would be my molar concentration for NaOH. Let's look at this example. If a beaker that contains 25 ml of 0.316 molar of a weak acid H2S is titrated with 0.125 molar NaOH. From here we could see that H2X is reacting with 2 NaOH, because I have here 2 protons, to give me 2 H2O plus X2 minus. In that case, the number of moles of NaOH would be equal to the molarity. I have to remember that the molarity is equal to number of moles over volume in liter. So in that case, I would multiply, if I need the number of moles, I will multiply the volume in liter in the molarity. So I have here this part of the molarity 0.316 molar multiplied by 25 mil, but I have to convert this one into liter, so I multiply here by 1 liter divided by 1 mil. And if I know that each 2 mole of NaOH is actually titrated against 1 mole of the acid, that would be equal to 0.0158. So this is the number of moles that I used. Now if I need the volume, so I have here number of moles, and I have here the molarity of the sodium hydroxide. Now can I get the volume? So the volume of NaOH would be equal to the number of moles which I obtained from that step, 0.158, multiplied by, so this is in mole, will be divided, actually not multiplied, this will be divided by the molarity of the NaOH, which is 125 mole. That would be equal to 0.126 liter. So sometimes the acid-base reaction actually results in the formation of a gas. Example for that, the reaction of sodium carbonate with hydrochloric acid. It gives 2 NaCl plus H2CO3. The H2CO3 actually decomposes into water plus carbon dioxide. Similar thing happens when potassium sulfide reacts with 2HCl to give me 2 potassium chloride plus H2S, hydrogen sulfide. So my next video will be on oxidation reduction reactions. Thank you and goodbye.